Image-based treatment effect, heterogeneity. Abstract. Randomized controlled trials, RCTs, are considered the gold standard for estimating the average treatment effect, 8, of interventions. One important use of RCTs is to study the causes of global poverty, a subject explicitly cited in the 2019 Sveriges Riksbank Prize in Economic Sciences in Memory of Alfred Nobel, awarded to Duflo, Banerjee, and Kremer for their experimental approach to alleviating global poverty. Because the 8 is a population summary, researchers often want to better understand how the treatment effect varies across different populations by conditioning on tabular variables such as age and ethnicity that were measured during the RCT data collection. Although such variables carry substantive importance, they are often only observed near the time of the experiment. Exclusive use of such variables may fail to capture historical, geographical, or neighborhood-specific contributors to effect variation. In global poverty research, when the geographical location of the experiment units is approximately known, satellite imagery can provide a window into such historical and geographical factors important for understanding heterogeneity. However, there is no causal inference method that specifically enables applied researchers to analyze conditional average treatment effects, CATEs, from images. In this paper, we develop a deep probabilistic modeling framework that identifies clusters of images with similar treatment effect distributions, enabling researchers to analyze treatment effect variation by image. Our interpretable image CATE model also emphasizes an image sensitivity factor that quantifies the importance of image segments in contributing to the mean effect cluster prediction. We compare the proposed methods against alternatives in simulation. Additionally, we show how the model works in an actual RCT, estimating the effects of an anti-poverty intervention in northern Uganda and obtaining a posterior predictive distribution over treatment effects for the rest of the country, where no experimental data was collected. We make code for all modeling strategies available in an open-source software package and discuss their applicability in other domains, such as the biomedical sciences, where image data are also prevalent. Introduction. Field experiments in the social and health sciences help us understand the effects of interventions in the natural habitat where people live. Their primary goal is often to identify the overall effect of a treatment TI on an outcome Y, marginalizing over units in the sample population, and thereby calculating the average treatment effect 8. By collecting tabular characteristics, XI, such as age and ethnicity, investigators can unpack results by subpopulations, estimating the conditional average treatment effects, CATEs. However, features in XI are often measured only at baseline, just before the experiment is initiated. Thus, XI rarely contain information on an experimental unit's historical characteristics, including its past neighborhood-level features and geographical context. Features which may be useful in identifying subpopulations that react differently to the same treatment. When experimental units I are associated with a particular location, satellite images, MI, can fill in this gap, providing important information about the otherwise missing historical neighborhood and geographical contexts. Indeed, in contrast to covariates measured during experiments, satellite imagery is collected passively from space for every geographic context on Earth. And thus, except for clouds covering the line side of a satellite, there is no systematic missingness in the data source. Moreover, these data have been collected for parts of the world since the Corona intelligence satellites of the 1950s, and for the entire world since the start of NASA and the U.S. Geological Survey's joint Landsat mission in the 1970s. The Landsat data are publicly available with a revisiting time of on average 16 days. Therefore, by combining satellite imagery with experimental data, researchers can investigate not only the historical and geographical roots of effect variation, but they can also predict how an intervention will likely impact places outside the scope of the original study, where no researcher-collected covariate data are available. That is, predictive distributions over treatment effects can be estimated not only for the experimental context, but also investigated in places not originally conceived of during the experiment, where no tabular background covariates were measured. In this way, Earth observation data have the potential to increase the applicability of ideas in casual transportability. However, despite the potential offered by images for causal inference, as evident by the growing literature, Castro et al. 2020, Chalupka et al. 2016, BA 2015, Scholkopf et al. 2021, Yi et al. 2020. Ding el, 2021 Passurek, 2010 Cadoreal, 2021 B. Huizos et al. 2017 Pawlowski et al. 2020 Lopez-Paz et al. 2017, it remains unclear how researchers should use these myths for CATE analysis. One key challenge is that MI is high-dimensional and rarely annotated. A CATE analysis using MI but relying on tabular methods, such as linear models or the generalized random forest Adel et al. 2019, would likely lead to poor interpretability or struggle to find heterogeneity within the high-dimensional image tensors. For these reasons, there is a major research need to form a causal inference framework for CATE analysis in images. Equipped with such a method, applied researchers would not only be enabled to start incorporating satellite images in future RCTs, but also reanalyze data from past experiments that have already been performed, with the goal of deepening understanding using satellite image data, potentially uncovering missed yet significant CATE, informing policymaking. In this article, we develop machine learning models, which characterize image-based effect heterogeneity in the RCT setting. We introduce an interpretable CATE model that employs Bayesian convolutional neural network arms, CNNs, with categorical gates that allow us to directly model mixtures of image clusters with similar effects. Our models estimate treatment effects for all units, conditional on treatment status, the image's MI, and, if desired, accounting for available XI by incorporating them into the cluster prediction or via orthogonalization. By residualizing, our model will identify what additional CATE that stems from MI, separately from XI, for enhanced heterogeneity analysis. The models construct image-type clusters that group units probabilistically based on their CATE similarity. In the following sections, we develop our methods, show some of their properties analytically, and explore others in simulated experiments. We demonstrate the usefulness of our methods by replicating the results of an RCT study in Uganda, the Youth Opportunities Program, YOP, Blattman et al. 2014. This study, conducted in 2008, was designed to help the poor break unemployment cycles by financially assisting their artisans and business activity. The government solicited young adults to participate in YOP, asking them to form teams and compose a business plan. After screening teams, the government randomly assigned some to receive one-time grants worth about $7,500, often more than members' joint annual income. Most of the applicants were young, rural farmers having low educational attainment, e.g. 8th grade, earning less than $1 per day, and working less than 12 hours per week. In many RCTs like YOP, the researchers collected a set of baseline covariates, but none of them explicitly capture historical neighborhood or geographical characteristics. Our replication uses satellite imagery collected independently of the original experiment and demonstrates the usefulness and limitations of using MI for CATE as a complement to the tabular version. While our contribution focuses on the use of satellite images in global poverty research, our methods are designed such that they generalize to other RCT settings where complementary image data are available. In the last few decades, there has been a rapid increase in the availability of imaging technologies. Most notably, these technologies are readily available in biomedical fields in the form of X-ray, positron emission, MRI, and ultrasound modalities. These images data streams are likely useful not only for estimating 8 Castro et al. 2020, Lopez-Paz et al. 2017, Chalupka et al. 2016b, but also for evaluating effect heterogeneity. More research will be needed to determine the usefulness of our modeling approach for such domains. Background and related work. CATEs with tabular data. Let yi of t denote the potential outcome of an intervention t in 0, 1 for a unit of study I. For example, yi of 1 may represent the poverty level in household I following an aid intervention, and yi of 0 is the level without intervention. We may define the unit-level treatment effect as tau I equal to yi of 1 minus yi of 0. When tau n is greater than 0, the unit's outcome is greater under treatment than otherwise. The quantity tau I cannot be exactly identified without strong assumptions. Because a unit can only receive a single treatment at a given time, only one of the potential outcomes, yi of 1 or yi of 0, is observed, and thus the counterfactual remains unobserved. Assuming consistency, that is, units comply with their treatment assignment, the observed outcome can be written as yi equal to yi of t, I equal to I of 1 times ti plus I of 0 times 1 minus ti, where ti denotes the random treatment status of I. The 8 captures the population effect by averaging over all unit-level effects. Average treatment effect, 8. E of tau I equal to E of yi of 1 minus yi of 0. The 8 is useful as it marginalizes over the heterogeneity present in a population to form an overall assessment of an experiment. With treatment randomization, 8 can be estimated non-parametrically by the difference between treatment and control outcomes, Rubin 2005. Despite the importance of aggregate quantities such as the 8, it is useful to disaggregate average effects using based on contextual information. Such a disaggregation is critical for not only scientific understanding, but also for policy learning, e.g., by personalizing treatments. This disaggregation can be a function of any type of general pre-treatment data variable GI, Conditional Average Treatment Effect, CATE, tau of G equals expected value of yi of 1 minus yi of 0 given GI equals G. The literature has primarily focused on conditioning sets that contain tabular data, xi, tabular conditional tau treatment effect. Tau of x equals expected value of yi of 1 minus yi of 0, given xi equals x, where x in R to the power of d denotes the vector of d pre-treatment covariates. For example, the generalized random forest is one such machine learning method, and it has proven useful in a variety of applied settings. However, these methods are tailored for annotated tabular data, and images are high-dimensional, often non-annotated. These non-annotated image features consist of image bands and pixels that may jointly induce effect heterogeneity. Thus, more research is required to improve the ability of investigators to understand CATE in the context of unstructured high-dimensional image data. Causal inference with image data. While most causal inference studies use tabular data, there is an increasing realization that image data provides a creative yet useful way to conduct causal inference. Castro et al. 2020, Ramachandra, 2019, Daoud and Dubhashi, 2020. To this end, there is a growing methodological literature investigating how images should be integrated to identify and estimate eights in the observational setting. Callas 2020, Kader et al. 2021 A. Pawlowski et al. 2020. Jerzak et al. 2023. Yet these approaches tend to mainly treat images as proxies for inclusion in the adjustment set, thereby securing causal identification. These approaches are not tailored for CATE analysis in images. Hence, little is known about how to use images for CATE. Like tabular information in XI, images as a whole or through its segments may be associated with treatment effect heterogeneity. In the observational setting, images MI could be part of both the conditioning and effect modification sets. In the RCT setting, MI is not a confounder since the treatment was randomized, but it may provide significant information for CATE as discussed in Section 1. In both settings, one target estimand is the image CATE, tau M equal to E1, E0, or MI equal to M, where MRWHD is an image obtained before treatment assignment, of width W, height H, and with D data channels. These data channels often contain reflectance information from various electromagnetic bands. In some applications involving Earth observation data, the I subscript may correspond to a spatially defined neighborhood, or to a person living in such a place. In applications involving medical imaging, the I subscript may correspond to patients or tissue regions. In both, the image CATE analysis will have a connection with multiple instance learning MIL, in the sense that a single effect response, e.g. high or low, may be associated with multiple image segments. For a review of MIL, see Folds and Frank 2010. Although image and tabular CATEs are both special cases of the general CATE, there are conceptual differences between them. First, images are unstructured, high-dimensional objects, and satellite images of each neighborhood are unique in RCT applications. This makes it difficult, if not impossible, to perform non-parametric inference. Second, since images are unstructured, it is unclear how to interpret the act of conditioning on an image. We need a conceptual language and modeling strategy for characterizing proximity between images in the space of conditional effects. Therefore, the remainder of our article will contribute to establishing this conceptual language for RCTs, leaving image CATE in the observational case for future study. Modeling causal effect heterogeneity in images. We first introduce a baseline method of interpretable image CATE analysis, which we will later contrast against the probabilistic image type effect cluster model, which will form the focus of our later application. Comparative baseline, prediction cluster CATE. In experimental settings, CATEs may be estimated readily by function approximation. Perhaps the simplest approach is to use a parameterized function, f sub y sub t of m, to predict potential outcomes, yi of t, of each intervention, a so-called t-learner. The CATE may then be estimated as hat tau of m equals f sub y sub 1 of m minus f sub y sub 0 of m. Shalit et al. Found that learning a shared representation used to predict both treatment outcomes improved prediction quality, and named this approach Tarnet. Given a CATE model formed by such function approximation, we can aim to increase the interpretability of the model output by partitioning units by their predicted causal effect, creating a clustering of inputs post hoc. This post hoc clustering will serve as a comparative baseline for the subsequent probabilistic models. Let F subcluster of hat tau of M is an element of the set containing 1, 2, to K denote a cluster labeling function determined by the output of hat tau, which partitions the space of effect sizes and, as a result, the space of images. C may be constructed by quantile binning of hat tau, or, as in our experiments, by K means clustering. The CATE with respect to the post hoc clustering labels is prediction cluster CATE. Tau of C equals expected value of yi of 1 minus yi of 0 given F subcluster of hat tau of mi equals C. In our experiments, we use the post hoc clustering of the hat tau of mi from Tarnet as a point of comparison, as the approach is a standard one for high-dimensional causal estimation. A drawback of a post hoc approach is that it compounds approximations to arrive at a discrete representation of treatment effect heterogeneity. If two similar images yield very different predictions due to misestimation in either the model for yi of 0 or for yi of 1, they are likely to be placed in different clusters. We would prefer to cluster images in a way that smoothly best approximates the image CATE in a single model. Moreover, it is difficult to quantify how the image affects the post hoc clustering, because it may be computationally prohibitive to propagate gradients through both the outcome and subsequent clustering model a topic explored in section 3.3. To address these limitations, we therefore develop a probabilistic image CATE model that directly targets the prediction of the heterogeneity itself in a low-dimensional summary, with the goal of increasing the interpretability of the image heterogeneity dynamics. Interpretable models for effect clustering based on image type. We now introduce a series of modeling strategies for directly targeting CATE clusters in images. To the best of our knowledge, this is the first work to use images to estimate CATE with a particular focus on interpretability. We will aim to fulfill the following criteria. 1. Model potential outcomes and treatment effects flexibly, e.g., allowing for nonlinearities. 2. Identify interpretable image clusters with similar in-cluster effect sizes and different cross-cluster effects. And 3. Allow for the modeling of uncertainty regarding the image clusters and treatment effects. Our target quantity of interest will be defined as follows. Image type CATE, tau of z equals expected value of yi of 1 minus yi of 0, given zi equals z, where zi is an element of the set containing 1, 2. K denotes the effect cluster of image mi, where there are K total clusters. We will search for assignments zi of clusters to images that best explain treatment effect variation. Because the treatment effects are decomposed by image type, there are only K quantities needed to effectively summarize the heterogeneity attributable to images. Since human working memory can track around 5 distinct chunks at a time, this low-dimensional probabilistic summary of the complex heterogeneity process stemming from images can in principle be communicated to human stakeholders, thereby facilitating future treatment targeting decisions. With this substantive motivation in mind, we now discuss how we meet the modeling criteria for capturing treatment effect heterogeneity with images. Probabilistic estimation of the baseline outcome. We satisfy the first criterion by allowing the baseline potential outcome, yi of 0, to be estimated flexibly as a function of the image. In particular, we let the mean of the baseline potential outcome, conditional on the image, be parameterized by a Bayesian convolutional neural network. Expected value of yi of 0 given mi equals mu of yi of 0 given mi equals m is distributed according to Bayesian CNN of m, where convolutional and dense parameters are not deterministic, but instead defined according to a distribution. This model for the baseline mean is listed as 2 in schema 1, and depicted as the arrow between mi and mu sub yi of 0, in the probabilistic model depiction in Figure 1. Effect mixture based on image type. Having defined the baseline, we next turn our attention to the modeling component that targets the image type CATE estimand. In this component, we first compute image type probabilities Pi using another Bayesian CNN. Given Pi sub z equals P sub z, the image takes on cluster type Z with probability P sub z. Intuitively, while the first CNN looks for image patterns indicative of mu sub yi of 0, the second looks for patterns associated with the type of treatment response. We develop two model variants for the type response characterization, one more interpretable and the other more flexible. Variant 1. Image type effect, cluster model here, conditional on the image type Z equals Z. Mean treatment effects are drawn from a normal with a mean mu sub tau sub Z and variance sigma squared sub tau sub Z indexed to that image type. We do not assume that there is a single treatment effect per image type, but instead that there is a specific distribution over treatment effects by image type. The cluster effect means and variances offer a complete summarization of this distribution. This model emphasizes interpretability. Given the image type, treatment effects are characterized by a single, unique distribution. Variant 2. Image type differential effect model. The first effect mixture model could be useful to investigators because conditional effects can be succinctly summarized with a small number of parameters, but in some circumstances, investigators may want a more flexible model for the heterogeneity structure. In that case, the distribution of treatment effects given the image type Z is parameterized by a Bayesian CNN arm indexed to Z. Mu sub tau given Mi equals M, Zi equals Z is distributed according to Bayesian CNN sub Z of M. Here, the image type acts as a stochastic gate that determines which image patterns will be used in predicting the mean treatment effect value given the image, Mi. There are several advantages to these modeling strategies. There is improved interpretability from summarizing image-derived effect heterogeneity in k-discrete clusters. Moreover, under the image type effect cluster model, we can efficiently summarize the cluster effects, see section A 1.21. Tau of Z equals expected value of yi of 1 minus yi of 0, given Zi equals mu sub tau comma Z. var of yi of 1 minus yi of 0 given Z equals sigma squared sub 0 comma Z plus sigma squared sub 1 comma Z plus sigma squared sub tau comma Z. Next, as the strategies are probabilistic, so we can explore uncertainty not only in the image cluster effects, but also in the cluster assignment probabilities. In addition, the cluster decomposition may facilitate scientific inquiry. An image type serves as a generalization tool for reasoning across images, facilitating theorizing about the causal mechanisms at play. Finally, we can readily compute the gradients of the expected cluster probabilities with respect to the image in order to identify how the image affects the typology, a matter explored in section 3.3. For both probabilistic model variants, estimation is performed via variational Bayesian methods, where we learn the joint distribution of the model parameters theta and the image clustering, Z, given the observed dataset. D equals open brace yi of ti mi close brace I equals 1 to n. Target posterior. P of Z, theta given D. Determination of salience regions in the posterior mean probabilities. One benefit of the Bayesian image type heterogeneity model is that we can examine the model in order to assess how image information translates into the predicted effect cluster. In particular, we can take the derivative of the posterior mean cluster probabilities with respect to pixel WH, S superscript direction subscript WHK equals the sum, from C equals 1 to C of partial derivative of expected value of probability of Zi equals K, given Mi equals M, with respect to M subscript WHC. Where C is an element of the set containing 1 to C denotes the channel band dimension. The quantity S subscript WHK is a scalar summary of how changing pixel WH would induce changes in the predicted effect cluster probability. Because the modeling strategy is probabilistic, the salience must average over the randomness in the predicted cluster probabilities, hence the expectation on the inside of the derivative. This expectation is approximated via Monte Carlo. Positive values of this quantity would indicate that increasing the pixel intensity at WH would increase the probability of cluster K. With the same logic, negative values indicate that increasing pixel intensity at WH would decrease the probability of cluster K. Because directional salience may not be interpretable when increasing the pixel intensity is not itself interpretable, we can also consider an approach based on magnitudes, bypassing the potentially difficult interpretation of pixel intensities in different bands. S superscript magnitude, subscript WHK, equals square root of the sum from C equals 1 to C of the quantity. Partial derivative of expected value of probability of ZI equals K given MI equals M, with respect to M subscript, WHC squared. Large values of S superscript magnitude subscript WHK reveal locations in the image that, if changed, would lead to large changes in cluster K probabilities. This measure is agnostic about whether those changes would be associated with increases or decreases in those expected probabilities. This salience information is difficult to compute for post-hoc clustering methods, as the clustering of the hat taus needs to solve a second optimization problem, as in k-means, through which gradients with respect to the initial outcome models may not be efficiently traced. Moreover, in contrast to the post-hoc approach of section 3.1, the salience measure here incorporates uncertainty in the cluster prediction itself, since the salience averages over randomness in the cluster probabilities. Policy action using the image-based heterogeneity model. A major motivation for considering satellite image-based CATEs is that we can readily generate predictive distributions over treatment effects for contexts outside the experimental setting and where no tabular covariates were measured by researchers, a possibility that may meaningfully expand the reach of causal analyses. In this context, for a new out-of-sample point not from the original dataset, I superscript out is an element of I of out. We form a predictive distribution over image treatment effects using P of tau subscript out given M subscript I superscript out, D equals the sum, from Z equals 1 to K, of the integral of P of tau subscript, I given Z subscript, I superscript out equals Z. Theta equals theta dot P of Z subscript. I superscript out equals Z given M subscript. I superscript out theta equals theta dot P of theta equals theta given D, with respect to D theta. We can use the predictive distribution over treatment effects to improve treatment targeting for out-of-sample individuals. With a fixed treatment budget of size n superscript O subscript 1 for the new dataset of size n superscript O, equals vertical bar 1 of out vertical bar, this policy can be written as pi of open brace M, subscript, I subscript out close brace, subscript I of out maps to open brace 0, 1 close brace superscript n superscript O. There are many approaches to this problem, and we refer readers to the relevant literature. Multimodal learning with image and tabular heterogeneity. Tabular information can be readily incorporated into this modeling pipeline. For example, tabular covariates can be appended to the input of the dense part of the cluster type and baseline outcome models. The resulting treatment effect heterogeneity clusters are therefore conditional on both individual level and also image context level information. This image and tabular data integration can be useful when investigators are focused on understanding the holistic heterogeneity dynamic in an experimental context, integrating both individual and neighborhood level information. Such a combined approach, an example of multimodal learning, can also be potentially useful in the medical domain, where image and high-dimensional medical records text can form the basis for improved patient response modeling. Distinguishing image from tabular heterogeneity. When tabular covariates were not measured, or when we aim to generate predictions for observations having no measured tabular covariates, it may be useful to perform image type effect clustering directly using images alone. When other tabular covariates are measured for the experimental sample, researchers may seek to understand the heterogeneity stemming from image information that is unique when compared with tabular covariates. For example, information about economic class is embedded in Earth observation images, since the urban poor are often concentrated in dense city centers, while the affluent often live in green space-rich areas outside cities. We may wonder about the remaining heterogeneity after accounting for tabular variables such as income. In this context, we can perform the image clustering on the orthogonalized outcomes, yi of t superscript perpendicular equals yi or t minus e hat applied to yi of t subscript I given x subscript I. The resulting clusters can then be interpreted as image effect types after accounting for the additive heterogeneity from measured tabular data. This image-specific decomposition can be helpful when geographic or neighborhood information is the focus of study. Treatment effect, cluster recovery in simulation. We now explore the dynamics of the proposed methods in simulation, where true treatment effects are known. We generate image-based treatment effect heterogeneity using H subscript I equals Gn, applied to max, applied to F subscript L, applied to M subscript I, H superscript plus subscript, I equals min, applied to H subscript, I superscript N subscript, I equals 1 plus sign applied to H subscript, I times absolute value of H subscript, I superscript 1 over gamma, where F subscript L denotes the application of a L times L filter to the image, max denotes the global maximum operation across the image, and Gn denotes a global normalization function scaling the H subscript I values to have mean 0 and variance 1 across the image pool. The specific transformation generating H superscript plus is selected to ensure all the treatment effects are in the same direction and to generate heterogeneity in the effect distribution, with greater bimodality in the treatment response as gamma approaches infinity. We let gamma equals 2. We define the treatment and outcome. T subscript 1 is distributed according to binomial of 0.5. Y subscript I equals T subscript I H superscript plus subscript I plus epsilon subscript I, with epsilon subscript I is distributed according to normal of 0. Nu times VAR applied to H superscript plus subscript Y. The value of Nu controls the extent to which the image is predictive of the outcomes, where smaller values indicate a stronger image heterogeneity signal. To explore the effect of the signal-to-noise ratio, we vary nu in the set 0.01, 0.1, 1. The filter used in the convolution function of equation 3 is visualized in figure A1, along with high and low responders from the set of images used in the simulation that we take from Landsat mosaics of sub-Saharan Africa. We have some degree of model misspecification here, as the way the data are generated is distinct from the estimation models. Given this, we will examine the degree to which the various models will recover key properties of the image-based causal system. Cluster recovery measure. We compare the estimated effect clustering with an oracle baseline from the true, in practice unknown tau subscript i's, that is, we first compute the oracle k, means clustering. Tau of z subscript oracle equals zth center from the oracle k, means applied to the true tau subscript i's. The clustering quality measure then compares the oracle with estimated cluster means. Cluster recovery r squared equals 1 minus the sum from z equals 1 to k of min, subscript z prime, of the square of tau hat, of z minus tau of z prime subscript oracle, divided by the sum from z equals 1 to k of the square of tau, of z subscript oracle minus tau bar subscript oracle, where tau bar subscript oracle denotes the mean across the oracle cluster centers. This measure is equivalent to the r squared in predicting the oracle cluster means from the estimated ones, where the ordering of the clusters has been arranged so that each oracle center is compared to its nearest estimated counterpart. Simulation results. We see in the left panel of Figure 2 one representative posterior distribution over y subscript I of 1 minus y subscript I of 0 given estimated cluster information. We find that the estimated clusters capture the bimodality present in the true distribution of tau subscript i's. The right panel shows how the cluster recovery measure for the image type differential effects model and Tarnit post hoc clustering are similar in the low residual variance setting. In the high residual variance setting, the Tarnit clustering struggles somewhat in recovering the oracle cluster centers. In contrast, the parsimonious image type effect clustering model performs best at recovering the clustering of the treatment effects across the noise range. This is encouraging for the application of the image type effect cluster model in practice, as presumably, the signal-to-noise ratio for real tasks involving Earth observation images is relatively high. Application to an anti-poverty experiment in Uganda. Data. In our application, we explored the effects of the anti-poverty experiment performed in Uganda and described in Section 1. The treatment variable is the random assignment of small teams to receive grants for business ventures. The outcome variable is an aggregate summary of skilled labor, CA 1.4.1, measured at the end of the experiment. 2 years after treatment assignment. De-identified outcome and treatment data were given voluntarily by subjects and are available under CC01 license. Longitude, latitude information about respondents' villages is found using OpenStreetMap. Pre-treatment image data are taken from Landsat. We use the orthorectified ETM plus pan-sharpened data product, processed to contain minimal cloud cover. Reflectance is measured in the green, near-infrared, and shortwave infrared bands. These bands are useful in capturing information about peak vegetation, water content, and thermal dynamics, in addition to structural land features. Empirical results. Due to space constraints, we focus on results from the image type effect cluster model, details in section A16. We set the cluster number to 2, after finding that cluster probabilities become highly correlated with additional clusters. The top 3 rows in the left panel of Figure 3 show results for the highest images having the highest posterior mean probabilities for cluster 1. For each image, this figure visualizes the salience measures defined in section 3.3. The bottom portion shows results for the highest posterior mean cluster 2 images. The effect for cluster 1 is substantially different than for cluster 2. Visually, we see that smaller effects exist for places with harsher terrain and less developed transportation networks, hampering economic growth. These low responders are found in the harsh mountainous northern part of Uganda. This is logical, as skilled labor tends to thrive in areas that are connected via transportation networks. Ashraf and Galore, 2011. We show in the right panel of Figure 3 how the results of the experiment may be generalized to the entire country of Uganda, assuming no systematic bias in places chosen conditional on the image information. In particular, we show the posterior predictive mean cluster 2 probability for the entire country. This kind of analysis can provide policymakers with potentially useful information for how to improve the targeting of treatments in the future across larger geographic contexts. The appendix contains supplementary analyses. For example, we show in Figure A4 the correlation between the estimated image CATEs and tabular CATEs, using various conditioning sets, as well as, in Table A1, between the cluster probabilities and other individual level covariates. We show in Figure A the images having the greatest uncertainty in the cluster probabilities estimated by the posterior standard deviation. In section A1.5, we orthogonalize the potential outcomes using tabular information, and the results remain similar. The correlation between raw and non-orthogonalized cluster probabilities is 0.85. Because our results remain similar after orthogonalization, the satellite images seem to supply independent and thought-provoking information about effect heterogeneity. Discussion and conclusion. Scientists and policymakers use RCTs to estimate population-wide effects CATE and subpopulation effects CATE, using tabular data collected at baseline, often near time to when the RCT is launched. However, these near-time variables tend to miss important historical or neighborhood-level features. While such features are often unavailable or expensive to collect, satellite images are a data stream that captures such characteristics in an unstructured form. As no CATE method exists explicitly for image analysis, this paper presents principles and modeling strategies for analyzing image-based CATE using probabilistic image type models. After deriving some model properties, we perform approximate inference using variational methods. Dynamics are explored via simulation. An anti-poverty field experiment from Uganda is analyzed, where we seem to find interesting heterogeneity. Our approach has limitations, which serve to motivate future research. First, our models estimate heterogeneity clusters at the image level, but not explicitly for smaller segments of an image. Having such within-image heterogeneity segmentation would further improve understanding of what in the image is generating heterogeneity. Second, our methods estimate heterogeneity with respect to a fixed baseline, i.e., the control intervention. While the choice of baseline is clear in most settings, in unclear cases, investigators may need to explore different baselines and compare results. Third, our model is tailored for RCTs, i.e., assuming unconfoundedness. More research is required to adapt it for observational settings. Using experimental data, effect estimates are confounding-free by design. Heterogeneity can be studied independently of identification. Observational data are more plentiful but require adjustment. Rosenbaum et al., 2010. We have also viewed images from solely the perspective of surrogate effect modification, in the language of Miguel and Robbins. The use of images as causal modifiers or mediators is left for future study. Finally, our focus on CATE for images opens exciting possibilities. It not only encourages others to start incorporating satellite images in their planned experiments, but also reanalyze past experiments, potentially unraveling previously undetected yet significant sources of effect heterogeneity. As demonstrated in our analysis of the Ugandan anti-poverty experiment, our method identifies heterogeneity not initially detected by incorporating informative satellite data. Thus, our image-based methods have the potential to contribute to policy by complementing traditional RCT heterogeneity analysis based on tabular SHE, and to analyses in other fields such as agriculture, disaster relief, climate science, and medicine, where image data are also prevalent.